Welcome back. We are doing imaginary numbers and roots today. So we've been working with quadratics. We have solved quadratics by graphing. We have solved quadratics by factoring. We solved quadratics using square roots and completing the square. We have one more way to solve square roots, and that is by the quadratic formula. So actually, I have this post-it that I made. Sorry, it got a little smeared. So the ways to solve a quadratic are by graphing, finding the x-intercepts, factoring, where we set it equal to 0 and we find the zero product property, helping us to solve it once it's factored. We can solve using square roots if it's only an x squared. Like right here, I can solve this using square roots because I only have an x squared. If I have x squared and x, I can't solve using square roots because I have to find a way to break them apart. So there we can use completing the square. And I have a little plus or minus here because in these we have to remember when we take the square root, it's positive or negative. And then the last way we're going to get into it is the quadratic formula, and the plus or minus sign is built into that for us. So today we're going to focus on talking about imaginary numbers and roots. We've been stuck. We can't take the square root of a negative number, but today we're going to figure out how to do that. And it sounds complex, but it's actually quite simple. What is really helpful is if you're good at breaking down roots. All right, so the graph here is f of x equals x squared plus 1. And this could be considered standard form or vertex form. And if I look at it in vertex form, I see that k is 1. So I took my parent function from 0, 0, and I shifted it up 1. And you can see that there's no x-intercepts. And typically when we solve a quadratic, not typically, always, when we solve a quadratic, we are trying to, again, find x when y is 0. And that's that big idea I keep bringing up. And when I graph, not every time will this graph hit the x-axis. And the x-intercepts are always a0. We're looking for the x value when y is 0, thus solving a quadratic. So there are no x-intercepts, so we would say here there are no real solutions. All right, and that's where we need to use these imaginary numbers. So I can't solve this by graphing, and I actually cannot solve a quadratic like this by factoring. It doesn't factor. So I have to use one of the other methods, square roots, completing the square, or quadratic formula. But we have to understand imaginary numbers first. And so I just want to remind you, if my quadratic hits two places, those two x-intercepts, I would have two real solutions. If my quadratic maybe just bounces off of it with the vertex, that's when I have one real solution. Anytime it does not hit the x-axis, whether it's down low or up high, I have no real solutions. And we're going to get into more of this as we do the quadratic formula and the discriminant. We are going to figure out how we know the types of solutions and what they are. All right, so let's get going into our world of imaginary numbers. We can solve this if we define the square root of a negative number, and that's why we have imaginary numbers. Otherwise, there's things that you couldn't do. You'd have to stop the problem because you can't take the square root of a negative. So the imaginary unit was invented. And we use I to represent the square root of negative 1. So that's one of the facts I need you to know. So I always tell you about making a note card. On your note card, you need to know that I is equal to the square root of negative 1. You're never going to leave a square root of a negative. You're always going to replace it with I. So here's that fact again. The square root of negative 1 is I. So here's a little example. We're using our rule. Remember that rule? The square root of a times b equals the square root of a times the square root of b? Well, we're going to use that rule. We're taking the square root of negative 2. We're breaking it down to negative 1 and a 2. Well, the square root of negative 1 is I. It's just a simple substitution. That's it. You've learned imaginary numbers. That's how simple they can be. Now, the square root of 2 is irrational, so we're going to leave it I square root of 2. That's how you say it. I square root of 2, or I times the square root of 2. Square root of negative 4. If I put the square root of 4 in my calculator, well, let me turn it on. Square root of 4. I get 2. Now we know that 2 squared or negative 2 squared is 4. But if I try to take the square root of negative 4, I get a domain error, meaning I cannot enter something with a negative number underneath the square root sign. That x is not defined. So to avoid that, we take the negative 1 times 4 and we break it up using our rule, and then we replace the square root of negative 1 with I, and since it's really I times 2, and to be proper, we rewrite it as 2I. And we're going to treat I just like we treat x or any variable. All right, now, here's the other thing that you need to have on your note card. I squared is just negative 1. So they're showing you this here. If I take the square root of negative 1 and I square it, doesn't the square root and the square cancel and leave me negative 1? Well, the square root of negative 1 is I. So if I square this side, I square that side, and that's where that comes from. So remember, anything you square, we have to consider if it's a square root squared, they're inverses. Just to remind you, if I told you to take 5 squared and then take the square root of it, that would be the square root of 25, which is 5. So just a basic reminder that square roots and squares are inverses, right? So in general, if I have the square root of negative b, that's going to break down to be the square root of negative 1, square root of b, and that's where the I comes from. And so I have someone who realizes, wait a minute, so if there's ever a square root of a negative, I'm going to have I in my answer. Absolutely, but the I is not underneath the square root sign. The square root of negative 1 is I. We get rid of the square root sign because we substitute it out. Now, if I have the square root of negative b squared, I get bi. Now, we have to be careful with this. This cancels with that, and that's why I get the negative b. So up here, when I do this, this example is the square root of negative 1 times the square root of b squared. That's why I have that I times b or bi. This cancels the negative 1 with the square root becomes I. This problem, the second one down here, that's the square root of negative b, and do you see how it's in parentheses? So the square and square root cancel, and I just get negative b. There's no I. So it's very important how the parentheses are placed also. All right, well, that was a little bit of time introducing it, so let's get into it. Express each number in terms of I, and I don't want any decimals, so we want exact answers, all right? No decimals here. So looking at this, I'm going to break this down as 3 times the square root of negative 1 times the square root of 16. Now, I have a habit of putting that negative 1 out first, and then if I need to work with the number, I will. And so what I have is 3 times I times 4. The 3 comes down, square root of negative 1 is I, square root of 16 is 4. And I treat I just like a variable. It's like an x at this point. 3 times 4 would come together, and I'd have 12i. All right, so let's look at this one. I've got, it says factor out the negative 1, so keep that negative, and this is what it means. Factor out the negative 1 by pulling it. Now, see that 75? I do need to break it up, so I probably would have jumped right to this step. 75, the biggest perfect square is 25, and then times 3. So we have to work with our perfect squares. All right, this is negative. These negatives cannot cancel. All right, they have nothing to do with each other. So I keep my negative number. The square root of negative 1 is I. The square root of 25 is 5. And the square root of 3 stays. Now, to be proper, we rearrange it. Anything that's not in the square root sign stays out front, but we're going to make it negative 5i times the square root of 3. Please make sure your I is not underneath the square root sign. Make sure it doesn't look like a 1, so it's an italic I or a little bit of a slant I. And we treat I like we would a variable. All right, so here are 3 check it outs for you to try. All right, hopefully you gave these a try. Pause the video if you didn't finish them. Pause that. But let's go ahead and go over this. I'm going to break this down. So square root of negative 1, that's the new thing. Then we need to break down the 12. Biggest perfect square is 4, and then times 3. So this becomes an I. Square root of 4 is 2. square root of 3 stays. Remember, it's all multiplication. We're using the rule square root of AB equals square root of A times square root of B. We're also using the fact that not I squared, just I, is equal to the square root of -1. So we pull off that negative. So I'm left here with 2I square root of 3. All right, this one, I'm going to keep that 2 out front, but I'm going to break up my root, square root -1. I'm going to leave that 36. It's a perfect square. So some of you can jump right down to it, and you're like, oh, my answer is just 12I. Where did I get that from? I don't want to move too quick that I lose things. It's 2 times I times the square root of 36 is 6. So there is your 12I. All right, don't be bothered by that -1/3. It's just going to hang out, and we'll deal with it. Separate that -1. I think you really want to pull that in its own root. And then we need the biggest perfect square that goes into 63. So I'm looking at 9 and 7. All right. Sorry about the bells. So here we go. I've got -1/3 times I times 3 times the square root of 7. Okay. I need to take and put my numbers together. So -1/3 times 3 is really -1I, keep the square root of 7. Or you might have simply -I square root of 7. So you can have a negative number. Negative number has nothing to do with the negative square root. Okay, so look, this had a negative underneath the square root. The answer is positive. This had a negative underneath the square root. The answer is positive. This had a negative under the square root, but because it had a negative out front, it's the overall negative number. These negatives don't cancel. You can't touch that square root of a negative. Okay, now let's take it one step further. We're going to go back to what we already did in 5-4, and we're going to solve equations and not be stuck when there's an imaginary solution. So before, if you had the x squared equals -81, you would have said, well, nothing squared equals -81. Think about that. 9 times 9 is 81. -9 times -9 is 81. There's nothing you can square and get a negative. Now, if I had something like negative x squared equals -81, then that negative sign would just cancel out, and I'd have x squared equals 81. But if I have this, I have to use imaginary numbers. So I'm going to come in and use all my tools. I've got the x squared isolated. I'm going to take the square root of both sides. So x equals, and then you have to remember, when I'm solving a quadratic, I should have those two answers, plus or minus, and then I have the square root of -81. So plus or minus, that'd be the square root of -1, and I'm going to keep that 81 as a perfect square, and I end up with positive or negative I times 9, which means positive or negative 9I. And there you go. So don't forget about the two answers, because positive 9 squared and -9 squared get me that same outcome. I can't check this because I can't put I in my calculator, so these are problems that I can't go back and check. Okay, we've got a quadratic. It's equal to 0. Notice there's only an x squared, so I can use square roots to solve this. They actually didn't tell us how to solve it. We could use square roots. We could try factoring, but we'd be stuck because it's an imaginary number. So I'm just using square roots when I can. It's quicker. But we could use a quadratic formula. But if I graph this, I would never see the vertex because it'd be 75 units high and graphed upward. So I'm going to subtract the 75 to isolate the x. Then I'm going to divide both sides by 3. So this is old news. We've done all this. So this is a nice review. But the difference here is I get -25, where before we would have gotten a positive. I'm still going to take the square root, but instead of just writing no real solutions, I can now write that it's a positive or negative 5i. And some of you can go right to that and you see it. If not, take a minute. First of all, we know we get the positive or negative because we took a square root, and we get the square root of -1 and square root of 25, and that's the positive or negative I times 5. Notice all my roots are gone, and that's my final answer. All right, let's keep going here. We have some problems for you to try. So this is where you're going to pause the recording and try these answers. Try these problems. All right, I'm going to jump in here. We're going to take the square root of both sides. So I've got x equals a positive or negative 6i. If you want to see it, that's the square root of negative 1, square root of 36. Again, I get my plus or minus. There's your I, there's your 6. Final answer. All right, we have a little more work to do in 2b, not too much. We have to move the 48 over. So I've got x squared equals negative 48. I now need to take the square root, so we're using our order of operations backwards. I get x equals positive or negative, so I'm going to go ahead and break this down. Square root of negative 1, then the 48 needs broken down. So I need that biggest perfect square. And I know that 4 goes into 48 12 times, but I want to remind you that that's not the biggest perfect square. You're either checking by going through a list, or you're breaking the 12 down to say, oh, look at these perfect squares. So 48 is 4 times 12, or 4 times 4 times 3. And that gives me 16 and a square root of 3. So there's my 48. Okay, final answer. Plus or minus 4i square root 3. All right, if you need that step in between, please do that. Oops, x equals. This is my I, that's my 4, so 4i square root of 3. Do you have the plus or minus on it? All right, last one, we're going to go ahead and subtract 25. So I have 9x squared equals negative 25. Divide both sides by 9. So that's gone. I've got x squared, and this is where you can't reduce this fraction. So try to reduce it. Don't divide it. No mixed numbers. All right, so if you try to reduce this fraction by putting it in your calculator, and you do, okay, I have 25 fraction 9, it's going to turn it into a mixed number. Some of you have a simplify key to hit. I don't want a mixed number, so if it did simplify, hit second and then your mixed number to improper fraction key, and it will turn it back to an improper fraction. So if it doesn't reduce, no decimals, no mixed numbers, we want the improper fraction, because I'm going to take the square root of it, and we have to deal with that. So now we're getting back to those roots and rationalizing denominators. The good news here is I don't need to rationalize the denominator. I'm going to get a positive or negative, and then that'd be the square root of negative 1 and the square root of 25. So the top would be 5i, and the bottom is the square root of 9. So I don't even have to rationalize that denominator. And that's my answer. You could also have it as 5/3 times I, because that's over 1. It puts it in the numerator. All right, let's keep going. We are talking about a complex number. All right, so we're talking about imaginary numbers, but now we're going to do a little bit more with them. A complex number is a number that can be written in the form of a plus bi. Okay, so you know those note cards I keep telling you about? I need you to have and write down that the complex number is a plus bi. All right, a and b are real numbers, and I we know is the square root of negative 1. And the set of real numbers is a subset of the complex numbers. Okay, so let me come here. Every complex number has a real part. That's the A, and an imaginary part. Oh, real part is A, and an imaginary part, which is the B, or I just write it as the BI. So there it is, A plus BI, real plus imaginary. So if we can go back way back earlier in the year, we talked about the real number system. That's what we talked about. We had a whole note card, and it was a real number system. And the real number system is split into rational numbers, irrational numbers. So if you remember the real number system, we had real, we had irrational. Underneath real, we had integers, whole numbers, and then natural numbers. But the only thing we didn't talk about were the imaginary numbers. So real numbers are one bubble with all rational and irrational. imaginary numbers are its own note card. So picture having our original note card of real numbers, and you have another note card of imaginary numbers, and we glue that onto a big piece of paper called the complex numbers. So anything that includes something from here and something from here would fit in the top there. Okay? So it defines that again. All right, real numbers, let me find this here. Real numbers are complex numbers where the b value is 0. All right, well that makes sense, because if I have a plus bi, that's a complex number. If I have a plus 0 times I, that's equal to a, so it's only real. So this is complex because it has the real and imaginary, and that's just a strictly real number. Imaginary numbers are complex numbers, so if it's imaginary, it's complex where a is 0. So if the a value is 0 plus bi, then that is considered a pure imaginary number. All right, so let's go ahead and see what we're doing with this. We are going to find complex roots of the whole quadratic function. So I am unable to solve this using just square roots. I can't factor it, it won't factor. I can't graph it. So my only options are to complete the square or the quadratic formula. And since we've done completing the square, we're going to go ahead and do that. So give us some time here. We have x squared minus 2x plus what? So we're going to use the rule to complete the square. All right, well, RB is negative 2. So I'm going to take negative 2 divided by 2, and then I'm going to square it. So that would be negative 1 squared, which is 1. So that's going to be the c value that I put in. So remember, when we complete the square, we isolate by moving the 5 over. So we have the ax squared and the bx and all the constants on the right. And when I go to complete the square, make it a perfect square, I have to balance my equation. So these little lines help. And then this needs to factor x minus 1. So this is a review of what we've already done. And that's x minus 1 quantity squared equals negative 4. Now before I was stuck and I wouldn't be able to solve this, but now that I've completed the square, I can come in and use square roots to solve it. Before it was no real solutions. Now I have x minus 1 equals positive or negative 2i. The square root of 4 is the square root of negative 1, square root of 4. And there's my I, there's my 2, I got my positive or negative, and now it's going to turn into a complex number because I have to add 1. When I add 1, it's proper to put it out front. So the real number 1 goes out front, plus or minus the imaginary part. And that is my answer. Again, I'm not able to take this and check it. I can't add the 1 and 2 because there's an I here, and that's just like adding unlike terms. Okay, so let's do this again. First thing is I'm going to set it equal to 0, x squared plus 10x plus 35. I think I'm going to put my 0 on the other side, but it doesn't matter which side your 0's on, but just since I don't want to throw anyone off, because I'm going to subtract the 35. So I'm building this to complete the square. I've got x squared plus 10x plus something equals negative 35 plus something. So what I like about this is we've introduced a new idea, imaginary numbers, but we're reviewing solving with square roots. We're reviewing roots and rationalizing denominator. We're reviewing completing the square. So we've got a lot of things we're doing. And this is where it all builds. So I need to put in my perfect square. I'm going to take b, which is 10, divided by 2, and square it. And even though I can do this in my head, I like to show it because whatever number I square, 5, is going to be my factor. So I'm adding 25 to balance it on both sides. This is going to factor to be x plus 5, x plus 5. Anytime we do this, we create a perfect square by taking half of this and squaring it. I put it in the two places to add it up to 10x. So what I have here is x plus 5 quantity squared, and that is equal to negative 10. All right, well, now that I have that, I have to finish it. So I'm going to come in and take the square root to cancel, just like we did when we solved using square roots, and complete the square. X plus 5 equals, I'm going to go with positive or negative, and then I have a square root of negative 1, square root of 10. Now, you want to double check and see you want to double check, sorry, my light's turned off. Double check and see if the 10 can break down, and it doesn't. So I'm going to have this as x plus 5 equals positive or negative I square root of 10, and then we finish it by subtracting the 5. So x equals negative 5 plus or minus I square root 10. So always the real a and then bi. Okay, I know this is getting a bit lengthy. Go ahead and try these two problems. Again, I can't use square roots. I could either use completing the square or the quadratic formula. I'm asking to use completing the square because that's what we've worked on. All right, now that you've tried these on your own, we're going to go ahead and do them together. I'm going to set it equal to 0. You could skip that step and go right to here, but please watch your signs. I like to leave that space because I know I'm completing the square, so I'm anticipating that, and I don't have to rewrite it another time. I'm going to complete the square by taking b, which is 4 divided by 2, and squaring it. So 2 squared is 4, and that's what I'm adding to both sides. Factor this, x plus 2, so important to write it as a quantity squared, and that is equal to negative 9. All right, now I come in with my square root because the whole quantity is squared. That's why I have to take the square root to get to that 2. And then I have x plus 2 equals positive or negative 3i. Square root of negative 1, square root of 9. Then I'm going to subtract 2. And again, it's proper to put that real part out front and then plus or minus 3i. Again, if the I wasn't there, then we would add this. Negative 2 and 3 is 1, negative 2, negative 3 is negative 5. But with the I there, you can't add it. These are not like terms. All right, let's go ahead and jump into this one. I'm going to go ahead with the x squared minus 8x plus 18, set it equal to 0. We're going to shift the 18 over. The reason we set it equal to 0 is we're trying to find x when y equals 0. Make sure you change your sign when you take that over. Okay, that's an easy mistake. Take and find your perfect square. So b, negative 8 divided by 2, and then square it. That's negative 4 squared, which is 16. So put the 16 in on both sides. I get x minus 4 times x minus 4 squared, and that equals negative 2. All right, I'm going to come in, and I have x minus 4 equals positive or negative I square root of 2. Square root of negative 1, square root of 2, right? There's your I, there's your square root of 2, and then add the 4. So just piece it together. Real part plus or minus stays with the square root, I square root of 2. Okay, last idea, stick with me. It's going to take no time at all, but we're going to use it later, so you can't forget this. So you know that note card I keep talking about? This needs to go on the note card. All right, it says find each complex conjugate, and I'm not sure why I don't have this earlier in the notes. I don't think there was a spot for it. But the idea of the complex conjugate is the opposite, okay? So if you have a plus bi, so these are sort of the notes here. The complex conjugate is a minus bi, all right? Now, one way you could see it, if you see a plus bi, and then you see a line over it, that line represents to find the complex conjugate of a plus bi. And that's all you're doing right here, okay? So the complex conjugate is basically you change sign of the imaginary number only. Change sign of imaginary part only. So this is out of order. If you want to rewrite it, it'd be negative 15 plus 2i, because that's how you would write it. And so the complex conjugate is negative 15 minus 2i. If you wrote it as negative 2i minus 15, that's fine. But it's proper to change the sign of the imaginary number. All right, the complex conjugate here would be 4i. That's it. Because it's 0 minus 4i, so 0 plus 4i. All right, so find the complex conjugate of these three numbers. This would be 9 plus I. This would be, let me rearrange, well, I don't want to rearrange it because of the square root, so I'm going to leave the I out front, but it's now negative, and then the square root of 3. So again, change the sign of the imaginary number. Negative 8I would become positive 8I. Okay, so just real quick, I know we're at the end. What would this complex conjugate do for us? It's not a random thing I'm teaching you. Let me show you something real quick. See that 9 minus I and that 9 plus I? If I would take those and multiply them together, isn't this a difference of squares? Same numbers, one plus sign, one minus sign. And so when I FOIL this, I get 9 times 9 is 81. I get an outside of positive 9 times I, the inside of negative I times 9, or negative 9I, and here we go, I get negative I times I, which is a negative I squared. What happens is those outer and inner cancel, so I'm left with 81 minus I squared. Now, we didn't work with this today, but oh boy, we're going to do some work with this. This I squared is really a negative 1. That was something that I said write down on your paper, and we showed earlier in this lesson. So this is really 81 minus negative 1, which becomes plus a positive, and I get 82. And by multiplying the original by its complex conjugate, I've canceled out I and gotten a real number. And why would I use this? If I have I in a denominator, let's say I have this in my denominator, I can't leave I in the denominator because it's a square root of 1, negative 1. So I can't leave a square root. So I multiply by the complex conjugate, and I do that to the top and bottom. And now this would be my new denominator, and my top would be 9 plus I, and now I have a rational denominator. So that was just a quick glimpse into something we're going to get into. All right, so imaginary numbers, not so bad.